Okay, welcome back. This is question 3. And what do we have to do now? And again, like I said, always beware that if it's a new question, new beginning of the question, as in this part's new, then it's probably going to change topic, or at least it might change topic. And it is changing topic. It's talking about electrical circuits now. So draw a diagram to show how 1.5 volt cells should be connected to give a potential difference of 4.5 volts. We don't have to actually draw the whole circuit here. We just have to draw enough cells. So a cell is part of a battery. So a cell would look like this. And you'd have, that would be the wire there. Whoops. Connecting it up. We want to know how can we combine a number of these. Each one is 1.5 volts. And how can they be connected together to give a potential difference of 4.5 volts? We just put 3 together, because when you so basically that's going to add up to 3. Now, do we have an eraser here? Oh, it looks like I can just do that. Okay. So altogether, this is going to be 3 times 1.5, so this is going to be 4.5 volts. All right. So basically, what I've used there is I've said that the V total voltage is equal to V1 plus V2 plus V3, and I could, if I had a fourth one, it would be plus V4. So what I mean by V1, V2, V3 is I mean the first voltage, the second voltage, the third voltage. And this works only in series, okay? So in series. So in series, we can add the voltages up, or the potential differences up, and it equals the total. Right. Now let's have a look at the next one. The student built the circuit in figure 3, so we've got an unknown resistor. It's always good to to make a prediction of what the question is going to be. So it's got an unknown resistor, we've got a known voltage, we've got a resistance over the known resistance, and we've got the current here. The current is going to stay the same all the way around the circuit. In a series circuit, the current stays the same all the way around. Calculate the total resistance of the circuit in figure 3. Oh, they're giving us the formula again. So again, I don't need to know anything. That's not good timing, is it? I don't need to know anything about the circuit, about electricity, to be able to answer this question, because I've got the potential difference, I've got the current. Well, I need to know that that's current, I suppose. Okay, fair enough. I need to know a little bit about electricity, but not much. Again, the reason why I keep saying these kind of things is because I want you to realize that there's many questions that you can answer without really knowing the topic that much. You can make lots of educated guesses, and it's worthwhile having a go at making those educated guesses. Never back down from a question. Give it a go. Just think about it. Imagine you just had to answer this question. Your life depended on answering this question. What would you do? So we've got resistance is equal to potential difference divided by voltage, and it was 12 divided by 1.6. So 12 over 1.6, and that is equal to 7.5. They've been very nice in giving the unit each time so far, but if they don't, just note that you need to write down the unit. If you can't remember the unit, guess. You don't lose any marks for guessing wrongly most of the time. I think maybe all the time. Right, the resistance of P is 3.5 ohms. They're walking you through the question now, and eventually you can guess. I guessed at the beginning that we have an unknown resistor. At some point, it's probably going to ask me to work out what that resistance is. So it's told us the total. We've worked out now that the total resistance is 7.5 ohms. Now it wants to know the resistance of Q. Well, in series, just like the voltage, R total is equal to R1 plus R2 dot, and so on, depending on how many resistors you got. So R total, which we worked out, we guided us through it, work out the total resistance is 7.5 ohms. So 7.5 ohms is equal to, well, one of the resistances is 3.5 plus this other resistor, which is, I've called R2, resistance 2. We can just write Q if we like. So what's Q going to be? Well, it's going to be, Q is going to be 7.5 take away 3.5, because what we're saying is, what do we need to add to 3.5 to make it 7.5? So, well, we can see from that, from thinking about it like that, it's going to also be, it's going to be 4. So, but just to show, because we're going to have to add 4 to 3.5 to make it 7.5. So 7.5 take away 3.5 equals 4. So that's what you'd write down. Oops, there. Okay, so 4 ohms. Right. Number 3.4. The student connects the 2 resistors in figure 3 in series. Sorry, in parallel. Okay, it's in parallel now, not in series. What does parallel mean? Well, we know that we know what parallel lines are. That gives you a clue, and it is possible to do a parallel circuit that doesn't have parallel lines, but they probably won't catch you out with something like that. But it gives you an idea that parallel. We got resistors. There's a resistor, and there's another resistor in parallel, right? So we put the wires in as well. We're probably going to see a circuit that looks a bit like this. There are 2 resistors. We can see they're in parallel. But what's it actually asking us? What happens to the total resistance of the circuit? Well, actually, the total resistance, when you put them in parallel, it decreases. Now, I'm surprised that this question is on a foundation tier paper, because some of my A-level students sometimes get this wrong. So why? But the understanding of it isn't too hard. So the reason for it is because there's the current going around. Now a resistor, we know, slows current down, makes it difficult for the current to travel. But and so it's going to. So when the current comes here, oops, it's going to go into there. Well, let's try that again. Okay. It's going to go there, and then it's going to, at this point here, it's going to split up. Oh, it's been very annoying. Okay. And then it's going to split up and go to those 2 places. So if there's a second resistor in parallel, what I've just done here is I've given the electricity a second option to go around the circuit. So rather than them all waiting for each other to go through this resistor here, half of them can go through this way, which means the flow of current will increase, and so the resistance goes down. How can I put that into a nice, easy sentence? Well, it's a 1-mark question. So more than one path for the well, it says charge in the mark scheme, but electrons or charge, let's put charge then. It's the electrons that are carrying the charge in this case. I'm sure you get away with writing electrons. For the okay, for the for the charge to travel. Flow is nice. Okay, that's question 3.